Greetings Physics 1 and welcome to your Calorimetry Lab. As always, I apologize in advance for the potato-like quality of this video and any cats that may enhance or interfere with our experiment today as they see fit. Today, for our experiment, we're going to be doing the calorimetry experiment exactly as it is in the lab, or excuse me, in the lab manual. In order to carry out this experiment, you will need a few pieces of equipment as follows: a thermometer, a scale, some hot water, and some ice. Now, I'm going to be going over specific instructions for what to do if you don't have, say, a scale or a scale that measures accurately, or a thermometer. For example, you'll notice that I don't have any styrofoam around the house, so I'm going to be using my coffee cup instead. And that because coffee cups aren't as insulative, or not as good at insulating heat as styrofoam is, I'm going to expect a slightly higher percent error, probably in the 6 to 10% range instead of the 0 to 5% range, that any of you able to perform this experiment with a styrofoam cup and a scale and a thermometer is going to be able to do. Now, the actual experiment is going to take place very, very quickly. You want to take your hot water, your boiling water, whatever you want to do, and you're going to pour it in to the cup and then dump the ice in immediately, and that's pretty much it. So this is what you want to do, all right? You want to make sure that your ice is just at right about the melting point. If you can get it somewhere in a glass or a bowl or something like that, so that it's just barely starting to melt, you'll know that it's at what temperature? The melting point, right? 0 degrees C. Okay, now if you've gotten that far and you've gotten some hot water in a cup and you have a thermometer and a scale, what you're going to want to do first is you're going to want to take the cup and put it on the scale so that you can measure the mass of the cup. And then you're going to pour your hot water in. At that point, you'll have the mass of the cup and the hot water, and also the mass of the cup. In order to figure out the mass of the hot water, all you have to do is subtract the mass of the cup from the mass of the cup and the hot water together. Okay, at that point, you're going to take your ice and you're going to dump it into your hot water. You're going to stir it around, make sure that it melts, and when it's done, you take the temperature. That's it. It has to be done very quickly. The longer that you take to do this experiment, the more mass of water you're going to lose as the water evaporates. Now, once you've gotten all of those pieces of information, the mass of the cup for 1, the mass of the cup and the hot water for 2, you subtract one from the other to get just the mass of the hot water. You take the temperature of the hot water before you throw the ice cube in. You take the ice, you wipe it off with a piece of paper towel or something along those lines, and you dump the ice into the hot water. And then you'll read from the scale what the mass of the cup, the hot water, and the ice are, those three together. You can figure out, of course, the mass of the ice from subtracting the mass of the cup, hot water, and ice from the mass of the cup and the hot water. Seems pretty straightforward, right? Now, if you've done it all correctly at this point, you had ice that was at about 0 degrees C at the melting point. And so it didn't have to warm up any to get to the melting point. And so as that ice melted, it's going to cool off the rest of the hot water. Now, this has to be done quickly, especially in the case of if you have a coffee cup like this instead of a styrofoam cup, because the styrofoam cup is not going to absorb as much heat as the coffee cup is, right? Also, you don't want to take a long time because the thermometer is also going to take up some heat if you leave it in there, right? In any case, if you know the final temperature, then you would be able to figure out how much heat the hot water has gained and how much heat the ice gained when it melted and then warmed up and found itself at thermal equilibrium with the hot water, whereas the hot water decreased its temperature and gave heat to the ice in order to first melt it and then warm it up so that the system is at thermal equilibrium. Everybody with me so far? Okay, now let's try and figure out what that actually looks like as far as the math is concerned, shall we? This is also in your laboratory experiment manual. So, for starters, if I can find what I did with my pen and my eraser here. Here we go. So for starters, what do we know? We know that the heat lost by the hot water is equal to the heat gained by the ice. Remember, energy has to be conserved, right? It can change in between types, it can go in between systems, but energy cannot be created or destroyed any more than matter can be created or destroyed in this universe, right? Let me try and center this just a little bit better here. Okay, now, how much heat did the hot water lose? Well, we know, that's Lucky, everybody. Say hi to Lucky. So we know what the initial temperature of the hot water was, right? We'll call that T hot. And we know what the final temperature of the system was, right? After we dumped the ice in and stirred everything around so the system came to thermal equilibrium. We'll call that T final. Now, how much heat did the water actually lose? Well, that depends on a couple of other things, right? Most notably, the mass of the water and the specific heat of water, right? So, the total heat that's lost by the hot water is going to be the mass of the water times the specific heat for water times the change in temperature for water, right? This is our good friend Q equals mc delta T. Now, we should be able to figure out the mass of the water by taking the mass of the water, the hot water, and the cup, and subtracting the mass of the cup, right? So we just have the mass of the hot water. We're going to multiply that by the specific heat for water and the change in temperature. Now, let's say, for the sake of argument, the mass was something like 50 grams. The specific heat for water, if we want to keep things really, really simple, instead of saying that it's 4.187 joules per gram degree C, let's just say it's 1 calorie per gram degree C. Keep it really simple, okay? So we're going to say C for water is 1 calorie per gram degree C. So C is just going to be 1, okay? If we're able to measure our mass in grams, great. If you end up having to do this mass in kilograms, as we'll see just a little bit later, that's no problem. Then this just becomes 1 calorie per or 1 kilocalorie, or 1,000 calories per kilogram degree C. Okay, no problem. In any case, the final temperature obviously is the temperature of the mixture when it's at thermal equilibrium. The hot temperature was the temperature of the hot water before the ice went in. Okay, Now, how much heat did the ice gain? Well, what happened to the ice? The first thing it had to do was melt, right? Now, the heat for melting ice is the mass of the ice times this thing we call the latent heat of fusion. The latent heat of fusion is 80 calories per gram. So, if you know the mass of the ice, which you could figure out by taking the total mixture, the ice, the cup, and the hot water together, right? Subtracting the mass of the cup and the hot water, you would get the mass of the ice. And we're going to multiply that mass by this heat of fusion. 80, that's calories per gram. Sorry, I never use calories. But this is simpler for our purposes. Okay, so now we've melted the ice, right? Well, that's not the only thing that happens to the ice, right? The ice is going to melt. Now it's 0 degrees C water, and that ice has to warm up to the rest of the mixture so that it can reach thermal equilibrium, right? Okay, so plus, we got the mass of the ice times the specific heat for water again, because now it's water and we're heating it up. And this time, we've got T final minus 0 degrees C, because the water, the ice, excuse me, was at 0 degrees C after it melted, and it warmed up to whatever our final temperature is, right? Okay. Now, we should then be able to predict the final temperature, right? It stands to reason, if we know all the rest of this stuff, we should be able to predict what the final temperature is. How can we go about that? Well, let me clear a little bit of room here. I'm going to rewrite this. I'm going to say MC and then T hot minus T final is equal to M times the latent heat of fusion. We'll call this M ice, maybe, just so we don't get it confused. And we'll call this M water. Plus mass ice, specific heat for water, and we got T final minus 0. Right? Okay. The next thing that we're going to do is we're going to find our terms that have our T final in it and try to get them all on one side. Okay? So we're going to have a mass water times C times T hot minus a mass water times C times T final equals mass of ice times latent heat of fusion plus mass ice times C times T final, right? Mass of ice times C times 0 is obviously going to be 0, right? So let's not worry so much about that right now. We want to get the terms with T final by themselves, so let's subtract this to the other side, and we'll add this to this side, okay? That's going to give us the mass of the water times the specific heat of water times T hot minus the mass of the ice times the latent heat of fusion. Right? That's going to equal, now we're going to take this term and add it to this side, the mass of the ice times the specific heat of water times T final plus the mass of the water times the specific heat times T final. Okay, now we've got a common term in these three terms. Fortunately, C is 1, remember? We specified that C is 1 calorie. Lucky. Well, you can't stand there, kitty. Come on. Come on. Thank you. So we already specified that C is 1 calorie per gram degree C, right? So because it's 1, let's just knock it out. That actually makes things a little more simple for us. I'm going to erase the top line here. And rewrite the bottom line. We've got the mass of water times T hot minus the mass of the ice times latent heat of fusion is equal to, okay, so we've got the mass of the ice times T final plus the mass of the water times T final. You'll notice that we've got T final in both of these terms, so I'm going to factor it. This is the mass of the ice plus the mass of the water times T final. Okay, finally. We're looking for the final temperature, right? Our theoretical prediction for what the final temperature should be. So, in order to make that prediction accurately, I'm sorry, I think Lucky knocked the camera a little bit. In order to make that prediction accurately, what do we got to do? We have to isolate the final temperature, right? So we're going to take this term here in parentheses, divide it over to the other side. That'll give us the mass of the water times T hot minus the mass of the ice times the heat of fusion, divided by the sum of the masses, mass ice plus mass water equals T final. Whew! In any case, this is exactly the equation that you should have in your lab manual. Now, most of the time, if you're going to be doing any kind of thermodynamics calculation, you don't generally want to use degrees C for hopefully obvious reasons. But because we're going from 0 to this final temperature, and we're only talking about the difference in temperatures, actually it works. Also, generally we don't use calories for hopefully also obvious reasons, but because we're only talking about the specific heat of water, it works. In any case, you take the mass of the water times T hot, you subtract the mass of the ice times the heat of fusion, and divide by the sum of the masses to get your prediction for the final temperature. This will be in degrees C. It works. Now, if you just so happen to have a styrofoam cup, a thermometer, and a small digital scale that you can use for whatever it is you do with one of those, you will definitely, as long as you do the experiment quickly, right? You don't lose lots of mass from water evaporating because the water is too hot. As long as you can take your measurements quickly, you will no doubt end up with a percent error of less than 5%. If you have all of these things and you get an error of above 5%, it means you probably did something wrong and you want to try it again. But I mean, it's pretty easy to set some water to boil and throw an ice cube into a cup, right? So if you have to do this, 2-3 times, it's not a big deal. Now, if you don't have a styrofoam cup, like I mentioned before, most likely you're going to end up with a slightly larger percent error. Hello, Ducky Meow. If you don't have a thermometer, that's going to be a little bit tricky. If you don't have a digital scale, that's also going to make things tricky. Now, what you can do in the case of if you don't have a digital scale, what you want to use instead is use a kilogram scale of water. Okay? I know that sounds like kind of a lot, but 1 kilogram of water is 1 liter of water. Okay? Because if you remember, the ancient definition for the gram for the cubic centimeter for the liter, all that is 1 gram of water is equal to 1 cubic centimeter of volume of water. And 1,000 cubic centimeters, or 1,000 milliliters, is 1 liter of water. It also has a mass of 1 kilogram. So, if you bring 1 kilogram or 1 liter of water to a boil, you will have exactly 1 kilogram of water. That can be your mass of water. If you have, I'm sorry, I don't think that came out very clearly. That can be your mass of water. For mass of ice, you can have 1 kilogram of ice as well. That's 2.2 pounds. So if you are going to go this route, you're going to need to freeze a whole mess of ice, like a lot of ice cubes, okay? If you really want to try to be clever about it, you can, instead of using 1 kilogram of ice, you can use half a kilogram of ice. If you really want to try to use pounds, you can look up the conversion. 1 pound, I believe, is 0.454 kilograms or something along those lines. But just be careful when selecting your mass for the mass of ice. Regardless, if you don't have a scale, but you still have a thermometer, taking the temperature is going to be simple, right? Now, if you don't have a thermometer, you're going to have to be much more careful, because you're not going to be able to test the temperature appropriately. The only real test that you're going to be able to do is if you stick your hand in the water after it's all become a solid, a single mixture at 1 thermal equilibrium temperature, is you can feel if it's hot, if it's cold, or if it's lukewarm. Now we all kind of know what lukewarm water feels like, right? If your water is lukewarm, that means it's body temperature. Everybody remember what body temperature is? I believe it's about 37 degrees C. Is that right? Why don't you all double check me? Yeah, about 37 degrees C. But don't take my word for it. Google it. You can use your own opinion, whatever you like. Now, if you're going to do that, that means your T final, what you're going to shoot for is a T final of 37 degrees C. Okay? If you're going to try to get a T final of 37 degrees C and you actually succeed, what should happen when you pour your ice into your water and you stir it and it comes to thermal equilibrium, you stick your hand in and it should be lukewarm. Now you want to be careful with this, of course. Obviously, don't stir with your hand if you're talking about hot water, especially if it was just boiling, okay? Just because we're on, what are they calling it? Shelter-in-place order. Doesn't mean you should go around burning your hand to a crisp. Instead, what you want to try to do is plan out your mass of ice and your mass of water appropriately so that you end up with a temperature of about 37 degrees C. Okay? You're going to want to back solve in that case. So you're going to want, instead of trying to isolate your final temperature, you're going to plan for your final temperature. You're going to say that this is 37 degrees C and isolate your mass of water and your mass of ice and figure out what those two should be. Obviously, if you're talking about boiling water, your T hot is going to be, correct, 100 degrees C. The heat of fusion will not change. That's still going to be 80 calories per gram or 80 kilocalories per kilogram. All you have to do then is figure out, instead of your final temperature, figure out your mass of ice and your mass of water. Okay? I'm going to spare you that calculation because you're going to have to figure that one out yourself. But please, do it carefully. Don't stir with your hands, stir with a spoon or something, okay? That's going to cause a slightly larger percent error, of course, but it's a lot better than getting your hand burnt. Now, the last and perhaps most important bit, if you don't have a thermometer, a styrofoam cup, a digital scale, and some apparatus with which to both boil and freeze water, you're probably going to end up with a percent error of greater than 5%. That's not the end of the world, and as you probably noticed so far, if you get greater than 5 or 10% error, it doesn't necessarily mean you're going to lose points. In fact, I'm pretty adamant about it not losing points as long as you actually know what it is you're doing. That's the important part, right? We're here to learn physics, not to crunch numbers. If you're actually going to get into career in science, you have plenty of time to try to practice techniques and run experiments with lower percent errors. Okay? If you end up with, let's say, an experiment setting where you have a scale and a thermometer, but you don't have a styrofoam coffee cup, you're probably looking at a percent error of about 10%. If you don't have a thermometer, and you have to try to do the lukewarm method, you're probably going to end up with something closer to maybe 20%. If you don't have a digital scale and you have to use the bathroom scale, and in so doing, you look up things by pounds instead, right? Then probably you're going to end up with, I don't know, 15 or so percent at minimum. It's not going to be easy. But if you can do better than that, then bully for you. There is always the possibility that you end up with a tiny percent error. As long as you keep things cool, mostly up here of course, and you stay focused. Alright? If there are any questions, of course, you can always email me. We'll get through this together. Alright? I hope you enjoyed this video as much as I enjoyed making it. See you soon.